As correct as Faraday was about electromagnetic induction, he was definitely also correct about taxing it. Because today, a modern 800 megahertz NMR spectrometer can cost you anywhere from $2 to $5 million. But we're not talking about the financial sufferings of magnetic resonance today. Instead, we're going to start building the classical magnetic intuition behind NMR. Because concepts like resonance, RF pulses, and spin precession, they don't make sense until we understand the magnetic world that these nuclei exist in. So the first thing we'll talk about is the magnetic field itself. To describe electromagnetic fields, we can either use the quantum or the classical description. Both of these actually work really well in NMR. The quantum description is more accurate, and eventually we'll need it, but due to its high complexity, we'll probably have to save that for another series of its own. So in the classical picture, electromagnetism is described using two fields. E is the electric field that interacts with electric charges, and B is the magnetic field that interacts with magnetic moments. And thanks to Maxwell's work in 1865, we know these two fields are deeply connected and they can be described by four equations, famously known as Maxwell's equations. Put simply, these say that electric charges create electric fields, changing magnetic fields create electric fields, electric currents and electric fields can create magnetic fields, and together, these fields can propagate through space as electromagnetic waves. And this is what light is. And the type of light that we exploit in NMR is radio frequency radiation. That's why we're always talking about RF pulses. But before we talk about RF pulses, we need to come back to the thing that magnetic fields actually interact with. We discussed this in the previous video a bit, and that's the nuclear magnetic moment. Now remember, a nucleus with spin behaves like a tiny magnet. And the magnitude of that tiny magnet is related to its spin by this expression. An important symbol here we kind of skimmed over last time is gamma, the gyromagnetic ratio. You can think of the gyromagnetic ratio as telling us how strongly a particular nucleus responds to a magnetic field. A nucleus with a large one is more magnetically responsive, it processes faster, absorbs at higher frequencies, and usually gives off stronger NMR signal. That's one of the reasons why proton NMR is so sensitive, and that's because hydrogen 1 has a large gyromagnetic ratio. Carbon-13, on the other hand, has a much smaller one. Now, gamma can either hold positive or negative values, and that sign doesn't mean that the nucleus is more or less magnetic, but it does tell us the direction of precession relative to the magnetic field. If gamma is positive, the magnetic moment precesses in one direction. If it's negative, it's going to precess in the other. So the sign controls the handedness of motion, while the magnitude controls how fast that motion happens. For these two spins I'm showing here, the left one is hydrogen 1, and the one on the right is carbon-13. And I'm exaggerating the difference visually, but the idea here is very much real. Hydrogen has a much larger gyromagnetic ratio than carbon-13, so in the same magnetic field, hydrogen precesses about 4 times faster. Okay, now I've been saying this word precession, so let's pause and understand what precession actually means. When people first learn that magnetic moments interact with a magnetic field, the natural thought is, okay, so why doesn't it just point along the magnetic field? And the answer is the magnetic field doesn't just pull a magnetic moment into alignment. It produces a torque. So instead of just snapping straight into the direction of the field, the magnetic moment rotates around that field direction. And that's the motion that we call precession. You can kind of think of it like a spinning top in gravity. The top doesn't immediately fall straight down because it has angular momentum. Gravity makes it wobble around the vertical axis. In NMR, the magnetic moment does something similar to that around the magnetic field axis, and the frequency of that motion is called the Larmor frequency, given by this equation you can see here. Gamma is given in radians per second, so if we want frequency in cycles per second, we'll just divide by 2 pi. This is one of the most important relations in all of NMR. It shows that the precession frequency depends on two things: the nucleus and the magnetic strength of the field. The nucleus because different nuclei have different gyromagnetic ratios, and the magnetic field because stronger magnets make the spins precess faster. So for hydrogen 1, gamma over 2 pi is about 42.58 megahertz per Tesla. For carbon-13, gamma over 2 pi is about 10.71 megahertz per Tesla. So hydrogen precesses about 4 times faster than carbon-13 in the same magnetic field, like I said before. That's why I said the animation I showed earlier was very much exaggerated, but not conceptually wrong. Because 42.5 megahertz per Tesla means 42 million revolutions around the z-axis per Tesla. The faster spin was hydrogen, but the slower one was carbon. So again, same idea. Now let's put some numbers into this. Suppose we have an 18.8 Tesla magnet. For hydrogen, gamma over 2 pi will be 42.58, and then the B field would be 18.8 Tesla. So this would give us about 800 megahertz. For carbon-13, on the other hand, the same magnetic field of 18.8 is applied, but the gyromagnetic ratio over 2 pi is now 10.71, and this is going to give us 201 megahertz. And this is exactly where we get the names of 500 megahertz NMR or 800 megahertz NMR. Instead of naming NMRs after their magnetic strength in Tesla, we're actually just naming them after the Larmor frequency of hydrogen in hertz. So an 800 megahertz NMR means that hydrogen precesses at about 800 million cycles per second in that magnet. Carbon-13 in the same instrument would not be 800 like we just saw, it would be around 201. But as far as naming goes, we'll always just go with the hydrogen's Larmor frequency. And the idea is simple. In the same magnet, let's say you have different nuclei, they'll have different gyromagnetic ratios, and therefore give you different Larmor frequencies. Now that explains the fast circular motion of individual spins, but there's something more important here as well. Individual spins precessing by themselves are not what we directly observe. In a real sample, we have an enormous amount of nuclear spins, and when we place that sample inside the magnetic field, spin populations become slightly biased. A few more spins will end up in a lower energy orientation than the higher energy orientation. And by slightly, I mean really extremely small, for a reason that we'll talk about in the next video. But simply put for now, the difference is tiny. But because there's so many nuclei in the sample, that small imbalance adds up to a small net magnetization pointing along the main magnetic field. So now the sample as a whole has a tiny magnetic moment along the z-axis. And remember, this is the sample as a whole, not the individual ones. As we talked about before, the magnetization is basically just sitting there, so there's nothing we can measure. And by Faraday's law of induction, he tells us that to induce a signal in our coil, we need a changing magnetic field. A static magnetic moment pointing along B0 can't be used for detection. So the trick in NMR is not to directly measure the magnetization along the main field, but to use an RF pulse to rotate the magnetization away from the z-axis into the plane that's perpendicular to the main magnetic field. That plane is called the transverse plane. Magnetization along this plane is called transverse magnetization. This is the part that we can actually detect. Because once the magnetization is in the transverse plane, it doesn't just sit still, it precesses around the z-axis at the Larmor frequency. So from the point of view of the receiver coil that detects the signal, the sample now has a tiny magnetic moment rotating in space. And a rotating magnetic moment produces a changing magnetic field, and that changing magnetic field is exactly what we need to induce an oscillating electric current in our coil. And that current that we see is what we get as NMR signal. But over time, the signal starts to fade, and you might wonder why. Because the spins don't stay perfectly synchronized forever. Tiny differences in the local magnetic fields experienced by the different nuclei cause them to precess at slightly different rates. At first, they're mostly in phase, but gradually they're going to start spreading out. And as they lose that synchrony, the net transverse magnetization starts to shrink. This decay is called transverse relaxation or T2 relaxation. The actual signal that we record is called the free induction decay, or for short FID. And it's called free because after the RF pulse ends, the spins evolve freely. Induction comes from the rotating magnetization that induces the current in the coil, and decay because the signal fades as spins lose phase coherence. So in the simplest classical picture, an NMR experiment does three things. First, the strong magnetic field creates a small net magnetization along the B0 axis. Second, an RF pulse rotates that magnetization into the transverse plane. And third, the precessing magnetization in the transverse plane induces a tiny oscillating current in the receiver coil. And that tiny current is eventually what becomes our NMR spectrum. And to some extent, everything else is just details.